Any of these circle theorem proofs could come up in the exam, and you should be writing down the sentences as we're doing it. Here we're going to prove that the angle at the centre is double that at the circumference. And the way you do circle theorem proofs is quite often we draw triangles that happen, because they both share the same radii, we happen to have some isosceles triangles. And because it's proof, we tend to use letters instead. Let's call this x. If that's x, then this is x, and you would write a sentence alongside the base angles of an isosceles triangle are equal. Angles in triangles add up to 180. So this is going to be 180 degrees, but I've got an x and an x which I don't want, so we need to take those away, minus 2x. We now move to the other triangle, which also happens to be isosceles, but I'm not sure that this is the same. So I'll call that one y. If that's y, then this angle here is also going to be y. Base angles of an isosceles triangle are the same. Angles in triangles add up to 180, but I've used up 2 y's. Then I know angles around a point, and here I'm looking at the centre of the circle, add up to 360 degrees. I've already got 360 degrees if I add together the 180 and the 180, but annoyingly I've got a minus 2x and a minus 2y which I need to compensate for. I'll add back in 2x plus 2y. And there's a posh way of writing 2x plus 2y. 2 brackets x plus y. We'll factorise it. And there we have proved the angle at the circumference, x plus y, is half that at the centre, 2 lots of x plus y. The proof for angles in a semicircle of 90 degrees is very similar to this proof. Again, it's all to do with forming some isosceles triangles. We don't know what this angle is, so we'll call it y. I'll call this angle y as well, because they are the base angles of isosceles triangles are the same, meaning this angle here must be 180, but I've used up a y and a y, so we'll take away 2 lots of y. Looking at this triangle, I can see we've got 2 radii. I'll call this one, now it's not going to be the same as y, so I'll call this one x. So this must also be x. The base angles of isosceles triangles are the same. Angles in triangles add up to 180, but I've used up 2 x's, so I'll take those away. I know we've got a nice straight line here, so 180 minus 2y plus 180, the angle at the right hand side, minus 2x, must equal 180 degrees. There's 180 on both sides. Let's take 180 from both sides. Now nobody likes grumpy y's and grumpy x's. They're being quite negative where they are. So what we'll do, we'll add 2x and add 2y to both sides. 180 is 2 lots of x plus 2 lots of y. And if I halve both sides, 90 equals x plus 1y. The angle in a semicircle, y plus x, is 90 degrees. This last one is the hardest proof, the alternate segment theory proof. First of all, the alternate segment, I always think of z's when I've got alternate angles, but with circles they never quite work the way they're supposed to. The z always points to the angle that's the same, so if that's x, then it's this angle up here that must be also x, and we're going to try and prove y now. Once again, it's to do with drawing on isosceles and equilateral triangles, or whatever triangles you can do. We know, and I would quote the rule, the tangent meets the radius at 90 degrees. So clearly this angle here is going to be 90 minus the x that we've used up. Hopefully you can see the isosceles triangle forming here. The two radii are the same, so this angle here must also be 90 minus x. Now angles in triangles add up to 180. I've got the 180 with the 90, add the 90. Annoyingly, I have a minus x minus x. I've got minus 2x that I don't want, so this must be positive 2x. Now this 2x angle is at the centre of the circle, and the angle at the centre is double that at the circumference, so all I need to do to prove the alternate segment theory is halve the 2x, giving me this angle here is x, and those two alternate segment theory angles are the same.